Okay, here's a Zoom meeting for Physics 232C. This week we're reading chapter 22 on wave optics. Last week was on geometrical optics, where we just described light in terms of rays of light traveling in straight lines unless they hit a boundary of some kind, in which case there can be reflection or refraction or both. Wave optics is different because in wave optics, we take into account the wave nature of light, the fact that light is not just a ray. There may be a direction of propagation, but it's actually made of electric and magnetic fields. Traveling along in that direction. So these crests and troughs, wave fronts, would be traveling along in the direction of the propagation. And what is the effect of these oscillations of electric field and a magnetic field? Magnetic field. And we saw in a previous chapter how these have to be moving simultaneously to make up the wave. So, taking into account that property of light, there are two questions to answer. What is interference? And what is diffraction? And those will be the major questions for chapter 22. Now, chapter 22 has a number of different sections, and any of these sections may provide a possible question for the next exam. For example, there's thin film interference. That's in section 1. There's two slit interference. That's the famous experiment done by Thomas Young, which really first proved definitively that light has a wave behavior. There's single slit diffraction. When light passes through an opening, it spreads out. That's called diffraction. And that has various consequences. There are diffraction gratings. If we make a surface with many openings or with many cut grooves, when light encounters that surface, the waves will spread out, overlap, interfere. There'll be constructive interference in some directions, destructive interference in other directions. The directions depend on the wavelength. And if we're talking about optical light, the wavelength determines the color. So light, white light, for example, coming from the sun, hitting a surface like this, will be perceived in the reflected light in all the colors of the rainbow. It's like looking at the surface of a CD or a DVD. There's also a section on polarization and scattering. Polarization is the fact that there's some direction of the electric field oscillations. That's called the polarization direction. It's some direction perpendicular to the direction of propagation. So if the wave is traveling this way, the electric field oscillations will be this way, perpendicular. The magnetic fields will be also perpendicular and perpendicular to the electric field. Well, that's the phenomenon of polarization. And then there's scattering. When light hits molecules or atoms, it behaves in a different way than when it hits a macroscopic surface. And that's called the scattering of light. So, for example, when sunlight hits molecules in the upper atmosphere, the sunlight is scattered, travels off in all different directions. And that scattered light is the sky. And as we all know, the sky is blue, although sunlight is not blue. Sunlight is white. But white is a superposition of all the different frequencies, and the higher frequencies are scattered more than the lower frequencies. Higher frequencies are in the blue and violet end of the spectrum. Lower frequencies are in the red and orange part of the spectrum. So this explains why the sky is blue, or why the sunsets look orange, because of the behavior of scattering of light by molecules in the atmosphere. All right, so there's a lot in this chapter. You should have already read the chapter and taken notes. The reading quiz is due tonight, and most people have already done the reading quiz. And now we come to the problem set. So what we'll do for the rest of the Zoom meeting is go over some examples in the problem set. Well, first, let's look at some of the equations. You can find the equations in the summary of the chapter on page 501. So read the chapter, take notes in your notebook, and when you're done, look at the summary and make sure you know all of the equations that you'll find in the summary. Here are some of the things you probably would write down in your notebook. Here's a picture of interference. This is thin film interference. This is interference where light hits an oil surface and reflects. But it can also pass through an oil surface and reflect on whatever is below the oil. So if you have a thin film of oil on, let's say, water, you can have light coming from above, scattering from the oil, or passing into the oil and scattering from the water. So you'll now have two outgoing waves. And where they are overlapping, there can be constructive and destructive interference. Some of the tricks of the trade when you're concerned with thin film interference is when light scatters from a more dense material, there's a phase change of 180 degrees. So in going from, well, it depends on what the index of refraction is. If the index of refraction of, let's say, water is greater than the index of refraction of air, then there'll be a 180-degree phase change. where this reflection occurs. Now, there would also be 180 degrees phase change where this reflection occurs. So the interference of the outgoing waves would be a maximum constructive interference if the path difference was an integer number of wavelengths. On the other hand, if this material, if this lower boundary here was different, there might not be a phase change, and then you would have you actually have destructive interference if the path difference was an integer number of wavelengths. So there are various things that can happen. Also, the wavelength in air is not the same as the wavelength in oil. So if you're given the wavelength in air, to calculate the constructive interference, you may need the wavelength in oil, which differs from the wavelength in air by the index of refraction. Or here is the example in section 2, double slit interference. You have waves coming in and hitting two openings in a opaque surface. Well, the waves will come out of the two openings, the two slits, and spread out because of diffraction. When a wave goes through an opening, it spreads out on the other side of the opening. And so from each slit, you have waves spreading out, and therefore they're overlapping. Where waves overlap, you can have interference. You can have, they're in phase, so that gives you constructive interference. In other words, brighter intensity, or they may cancel each other, giving zero intensity. So if the light is collected on a screen over here, you'll see interference fringes. You'll see alternating regions of bright and dark, bright, dark, bright, dark, bright, dark. Bright is where the waves from the two slits interfere constructively. Dark is where they interfere destructively. The formula for the direction, the angular direction of the bright fringes is d sine theta. D is the distance between the slits. D sine theta is an integer number of wavelengths. That's because the path difference would be d sine theta if the screen is far away. And if the path difference is an integer number of wavelengths, then the two waves will be in phase. One will be there and one will be there. So, where they're both at a maximum, you have constructive interference. That means the path difference has to be an integer number of wavelengths. Diffraction is another part of the chapter. Waves spread out as they pass through an opening. So you can have diffraction gratings where you have many openings for light to go through, and light from all those many openings will spread out, overlap, and interfere, giving you some directions where you have bright fringe of light, and in between the bright fringes, you'll have dark fringes of light. The angle for bright interference or for constructive interference or destructive interference, that angle depends on the wavelength. So for example, bright fringes from a grating are given by this relationship where m is an integer, lambda is the wavelength of light that you're considering, d, I guess, is the distance between the slits of light in the grating, the distance between one opening and the next. And sine theta, well, theta is the angle that the waves are coming off the surface. That's for two-slit interference or multiple slit interference. You can also have interference from a single slit, and that's called single slit diffraction. You have a similar kind of equation, but this is, in one case, for bright fringes. This is the formula for dark fringes when light goes through a single slit. Another topic that's considered when in the section on diffraction is Rayleigh's criterion for angular resolution of a telescope or a microscope or your eye. The resolution in an angular in radians is the number 1.22 times the wavelength over the diameter. We'll see an example of that in one of the problems. All right, so here's a problem from the assignment, which is due Wednesday, on Newton's rings. So a Newton's rings apparatus will be observed with yellow light. Let's say the wavelength is 575 nanometers. What's the minimum air gap to produce a bright ring? Well, actually, it changes that's problem 30 in the book, but the number will be changed depending on which student is solving the problem. Now, here's how Newton's rings works. You have a half of a lens, a hemispherical little piece of glass, resting on a very flat piece of glass, a plane of glass. Now, light coming in from above, well, it can reflect off the circular arc of this lens, or it can pass through the lens into the air and then reflect off of the top surface of the flat piece of glass. And so you have here two interfering waves that went different distances. And since they went different distances, they have shifted whether they're in phase or out of phase. So they've shifted their they've shifted the position of their maxima and minima, their waves and crests. So here it's drawn again. In the case of Newton's rings, the lens on the top has a varying thickness that depends on r, the radius from the center. And you can have reflection from inside the lens. So that's interior reflection from inside the lens. And you can have reflection from the glass surface. So here will be two outgoing waves overlapping and interfering. Now, you might say that if the path difference is one wavelength, then you would have constructive interference. So suppose one wave is like this, and the other wave is like this. You see, they've shifted by one wavelength. So that's the path difference. One wave is a little longer than the other because it had to go through the region of air. And now, if they're in phase, then that'll be a bright ring, constructive interference, because where one wave is a maximum, the other wave is also a maximum. So when you superimpose the waves, you'll have twice the maximum. Or where one wave is a minimum, the other wave is a minimum. So when you add them together, you'll get twice the negative value. Now, it's actually not quite that, because there's a 180-degree phase change for light reflecting from air into glass. So here, light is going from air into glass, and there's a 180 degrees extra change of phase on that reflection. But here, the light is going from glass into air. And so there is no extra phase change. So if the path difference was one wavelength, when they come out, they'll be out of phase because of that extra 180-degree phase change. So if the path difference, now the path difference will just be 2 times the air gap, because the extra distance that the second wave has to go is through the air gap and then out again. So it's got this extra distance 2y that it has to travel. So if 2y is an integer number of wavelengths, then because of the extra 180-degree phase change, you'll have destructive interference. That'll give one of these dark rings. On the other hand, between the dark rings, there'll be bright rings. So destructive interference has y is, let's say, lambda over 2. But if the air gap is lambda over 4, then you'll get constructive interference. So the answer to the question, what minimum air gap will produce a bright ring, will be lambda divided by 4. So you'll have to read the section on Newton's rings and thin film interference that has the same kind of problem. There's an air gap that's a kind of a extra distance. If that's an integer number of wavelengths, the waves should be in phase unless there's an extra 180-degree phase change, in which case they would be exactly out of phase. Here's a problem related to Young's experiment. Okay, an important experiment in physics was Young's double slit experiment, which proved really that light consists of waves. Because as light goes through two slits, as it goes through the slits, it spreads out, that's diffraction, overlaps, and there can be overlapping regions for constructive interference or destructive interference. Now, this problem involves doing Young's experiment with microwaves. So you have here, so here's an antenna producing microwaves. And here's an antenna receiving microwaves and measuring how strong they are. And as you move the receiver around, you'll get alternating regions of high intensity and low intensity. Those are like bright fringes and dark fringes. So here are the two slits. So as the microwaves come through these two slits, they interfere because of diffraction. As they go into the horn of the antenna, they can be constructively or destructively interfering, giving you a large intensity or a small intensity. So let F be the frequency, A be the separation of the slits, so this distance is A, and D the distance to the receiver, so I guess this distance is D. All right, so here's the explanation of two slit interference. You have these waves, which are coming from the transmitter, passing through the two slits, spreading out by diffraction as they go through the slits, overlapping and interfering. So in some regions, you'll have constructive interference, that'll be high intensity. Between those regions of constructive interference, you'll have regions of destructive interference, that's low intensity. The central angle will be a region of constructive interference because a wave coming from here to here and a wave coming from here to here, they would be in phase. And so they would add, making high intensity constructive interference. So there'll be a central maximum and then alternating maximum, minimum, maximum, minimum, maximum, minimum. So that's the picture. Now to analyze, you look at this little diagram, you look at the path difference. You draw a line connecting the two outgoing waves from the two different slits, perpendicular to those two slits. The screen is far away, so that's more or less in the same angular direction. Then there'll be an extra distance for the wave through the second slit. That'll be A sine theta by this little triangle here. The hypotenuse is A, the opposite length is this ds. So ds is A sine theta. So that's the path difference. And if that's an integer number of wavelengths, then you'll have constructive interference. So here's the equation for constructive interference. The path difference is n lambda. And there's no extra phase change from reflection because there's no reflection here. Just waves passing through these two slits. So the condition for constructive interference is n lambda is ds. The smallest ds would be lambda, delta s. Now, what are you supposed to calculate here? I guess it's this. calculate the angular distance between maxima. So we have the equation A sine theta equals lambda. That's for the first constructive interference, or A sine theta 2 is, I shouldn't say lambda 1, I should just say lambda is 2 lambda, set n equals 1, set n equals 2. Calculate the angular distance between the maxima. So I want to know theta 2 minus theta 1. That's the unknown. So these angles will be very small, so I can approximate sine theta by just equal to theta. I can just say theta is n lambda over A. So delta theta, theta 2 minus theta 1, would just be lambda over A. Whoops. Now, I'm not told lambda, but I am told F. So I have to remember lambda is the speed of light, the speed of the microwaves. All electromagnetic waves travel at the speed c in empty space. So lambda would be c over the frequency, and then divide by the distance between the two slits, A. Okay. Here's another problem. A red laser is aimed through a circular pinhole. Well, when light goes through an opening, it spreads out. And as it spreads out, it overlaps. The waves overlap, so you can have constructive and destructive interference. So for a circular pinhole, so the laser is way over here someplace. Here's the wall, which is like a screen. The laser light goes onto the wall, but it went through this little pinhole here. And so here will be the constructive and destructive interferences for waves that diffracted through the hole, the pinhole. And in the diffraction pattern on the wall, what's the distance between the central bright spot? That'll be equal distance all the way around. So that'll be constructive interference at the center. And the second dark ring. So the second dark ring would be, I don't know, here's central spot, dark ring, dark ring. So it would be this distance, I guess. Well, we're going to change this because this textbook doesn't have light passing through a circular hole. It has light passing through a narrow slit. So we're changing the problem here. Assume the aperture is not a circular pinhole, but a narrow slit with a width W. So here's a kind of a view of these waves coming in towards this slit. It's a slit in some kind of opaque surface. And then the waves will spread out by diffraction. And we can look at a particular direction. So we can look at some direction theta. The central position will be at maximum intensity. And then there will be alternating minima and maxima. And we want to look at the second dark fringe. So here's a graph of the intensity versus the height on the wall. The central spot is here, and then there's alternating dark and bright fringes. So we're looking for the second dark fringe here. So we're looking for this distance from the central spot to the second dark fringe. Now, actually, we're told the wavelength, we're told the distance to the wall. We're also told the distance between the central fringe, the central bright spot, and the dark fringe we're interested in, 2.55 millimeters. So what's the unknown? Well, the unknown is W, the width of the slit. So here's the picture. Here are the equations. The path difference is W sine theta by trigonometry. If I look at this little right triangle here, the hypotenuse is W. The extra distance is delta S. And this angle is the same as this angle. So W sine theta is delta S. If that is an integer wavelength, then that'll give a dark fringe. Because let's say this region would be positive, this region would be negative if the path difference was an integer number of wavelengths. In other words, let's say it's one wavelength. So the wave looks like this. Over here, it's positive. Down here, it's negative. Well, when you combine those, they'll cancel. So that'll give you destructive interference, a dark fringe. So the condition is that delta S, which is W sine theta, is m lambda, where m is an integer. M could be +1, -1, +2, -2, +3, -3, any integer. And now we want to calculate y, I guess. Looking at this triangle, y is L tangent theta. Looking at this little right triangle and applying trigonometry, y is L tangent theta. And we want to consider m equals 2. So we have W sine theta 2 is 2 lambda, and tangent of theta 2 is y2 over L. The unknown is W. So if I put these equations together, W will be 2 lambda over the sine of the arc tangent, y2 over L. y2 over L is the tangent of theta, so theta is the arc tangent of y2 over L. So that's a couple of examples of diffraction and interference. Let's look at this problem number 73. A spy satellite. Suppose a spy satellite is in a circular orbit around the Earth at a height h above the surface. So we're going to draw a picture. So here's the Earth down here. Here's the orbit of the satellite up here. And here's the satellite at some particular point time. And it's at a distance h above the surface of the Earth. Let's say it has a diameter d, and it can resolve surface of the Earth with linear dimensions q. So this distance is q. In other words, this little telescope here, which has a diameter d, so light from the object that it's looking at, so light is coming in here to the telescope with a very small angular separation. The linear separation is q. Now, when light passes through an opening, like the opening in the telescope, it spreads out. And so there's a limit for the optical resolution. Limited by the diffraction. You know, if one part of the object here makes an image like that, and the other side of the object makes an image like that, well, you can't really tell if that's one or two things. It just looks like one thing. So you can't really resolve distances which are at a small angle. That angle is called the Rayleigh criterion. So you'll read about this in pages 495 to 496. Probably got this written down in your notebook. The Rayleigh criterion. It says the sine of the angular resolution is a certain number, 1.22, and then the ratio lambda over d. Lambda is the wavelength, d is the diameter. So this is wavelength divided by diameter. And this applies to all kinds of optical instruments. The larger the diameter, the smaller the angle you can resolve. But for a given diameter and a given wavelength, there's a limit to how small an angle you can differentiate. You know, can you tell these two angles apart? And Lord Rayleigh worked out that you can't really separate them if their angle is less than theta r, given by this criterion. So how do we solve this problem? Well, we want, first of all, what's the angle? That's the angle theta r. It's q, or rather q over 2, divided by h. So q over 2 divided by h is the tangent of theta r. I guess I'm going to call this distance theta r, so this part would just be theta r over 2. So q over 2 divided by h, by, again, trigonometry. Look at this little right triangle here. It's the tangent is the opposite, which is half q, over the adjacent, which is h. Now, that'll be a very small number for a spy satellite, so I can just approximate that by theta r over 2. Now, let's say that diffraction limits the optical resolution to this linear size q, then calculate what the diameter of the spy satellite has to be. So we're going to solve for d. So you see d, bring this over to the other side of the equation, divide through by sine theta. So d is 1.22 lambda over sine theta. Sine theta is about the same as tangent theta. Tangent theta will be q over h. So d will be 1.22 lambda divided by q over h. And now, is your answer reasonable? I mean, NASA, or actually the Pentagon, puts spy satellites in orbit around the Earth so that they can spy on, I don't know, Russia or China. Suppose they want to be able to resolve things the size of a car, or maybe 1 meter. Suppose they want to resolve things by about a meter. How far should it be above the surface of the Earth? Well, I don't know. This suggests 300 kilometers. Actually, this proposes Q much less than a meter. So you can actually see things smaller than a car. Well, lambda is a small number, let's say 555 nanometers. Q is a kind of middle-sized number, 15 centimeters. H is a large number, 300 kilometers. When you combine all these numbers, do you get a number that makes sense? Or is the spy satellite going to have a diameter of 1 kilometer? You know that's not possible. Or can it be as small as 1 centimeter? Well, no, certainly you can't put a 1 centimeter size spy satellite and expect to be able to resolve everything. So, you know, what's the answer? Well, you're going to give a number, and the question is that reasonable? You can sort of guess how big is a satellite? How big is the telescope you put inside a satellite? Should come out to be something reasonable. Here's an example with thin film interference. You have oil slick on, let's say, wet asphalt. So you have an oil slick. So there's the oil. And it's on some other kind of material. Let's say could be on water, could be on asphalt. Let's say it's on wet asphalt. So I guess you could say it's on water. Light is coming in from above. It's coming in from the sun. So sunlight is hitting a little oil drop here. So here you have the street, and I have a little drop of water here. And sunlight is coming in. It can reflect off the top of the oil, or it can reflect off the bottom of the oil. So you have here two sources. They'll spread out by diffraction. They'll overlap. They'll interfere. And so you'll have interfering. Now, of course, the sunlight is white, which is all the wavelengths. So the outgoing waves here will have all the different wavelengths. And at some angles, you'll have constructive interference for a given wavelength. So, you know, out here, you'll have constructive interference in blue. In here, you'll have constructive interference in yellow. So you'll get a kind of a ring of the colors of the rainbow. Everyone has seen this. You know, if you've walked around a street, cars are constantly dripping little drops of oil onto the street, and you'll see these little oil slicks. Now the question is, what's the thickness of the oil slick for a given wavelength? 507 nanometers, that would be kind of yellow. There'll be interference if the thickness here, that's the thickness of the oil slick, that thickness, call that tau. If 2 times the thickness is an integer number of wavelengths, then the two waves coming from the top of the oil and the bottom of the oil will interfere constructively. And so you'll have a bright ring of yellow light. So you need 2 times the thickness to be the wavelength. Now that's the wavelength of the waves in oil, because the waves here are passing through oil. But when you say that the wavelength is 500 nanometers, that presumably means in air. So that's not the wavelength in air. That's what you're being given, 570 nanometers. So you'll see if you read through the chapter that there's a relation between wavelength and index of refraction. So the wavelength in air would correspond to n equals 1. Index of refraction of air is almost 1. The wavelength in the oil would be C over N, where N is the index of refraction of the oil. I guess that's N1. And what's to calculate tau? So it's a short calculation now. Okay, so that's all I have for today. And that's chapter 22. And the assignment is due on Wednesday.